name is Spencer. I'm a PhD student here at the GRASP lab. And today I'm going to give you a brief overview of some of the research I've been doing for my thesis over the past couple of years. And I'm going to start off my talk, if it goes to the next slide, talking about flying cars, because I think that's an exciting thing. I think a lot of people growing up, they dream to have their own personal flying car. And American pop culture has been obsessed about flying cars for decades now, pretty much since the invention of cars and airplanes. It's 2025 now, and we don't exactly, I didn't check today, but I'm pretty sure we don't have flying cars. But I will say, we've never been closer to having this dream of flying cars and be able to fly from your home to your job in the city and back, no traffic whatsoever. We've got a lot of exciting companies that are working on reinventing the helicopter, essentially, but developing these personalized aerial vehicles that promise to be quieter, safer, easier to use, etc. On the other side of things, we've got a lot of drone companies that are actually piggybacking off of the success of platforms like PX4 to develop autonomy for package delivery, for instance, right? For flying packages from one situation to another. But I really think that the elephant in the room here, that something that's really going to be a problem in the next 10 to 15 years is urban wind. The fact that you have all of these skyscrapers, buildings, bridges, these bluff bodies that are interacting with the atmospheric boundary layer are going to create a lot of very complex flows that, frankly, I don't think any urban air mobility or package delivery drone company is trying to attack right now. And that makes sense. They're just trying to get their prototype in the air. But I think as we try to introduce these prototypes into our nation's airspaces, one of the biggest challenges in my mind is going to be these urban wind phenomena. So the problem that I'm trying to address with my thesis work is wind, right? Wind is a clear danger for these autonomous aerial operations in dense urban environments. And I believe that urban air vehicles, in order to be successful and safe, need to be able to perceive the wind and make proactive decisions in order to avoid these dangerous and costly wind conditions. However, as I'll show very briefly, a lot of existing methods that try to solve this problem suffer from computational intractability, privileged knowledge about the map, or require significant amount of exploration and/or sensor infrastructure in order to enable these methods. So in my talk, I'm going to cover sort of 3 chapters of my thesis in a way. I'm going to talk about a novel method for local wind prediction using navigational sensors. And then I'll talk about using that enhanced capability and that enhanced situational awareness to enable safer and more energy efficient flight through urban environments. And then last, I'll kind of talk about our progress towards validating some of these ideas on actual hardware platforms. And the main focus with all of my work is developing methods that could, in theory, be applied in real time using onboard sensing. So I'm going to start by talking about some work on local wind prediction. So the problem is, we've got this very complicated flow phenomena that, again, as I said, arises as that boundary layer interacts with all of these bluff body buildings in an urban environment. And the question is, how do we put together an accurate model of this flow? Because if we had an accurate prediction of what the wind would look like, that would kind of trivialize the problem in a sense. And so one kind of brute force option is to do something like computational fluid dynamics, where, this is pretty standard stuff. We're simulating the wind using existing numerical solvers and some sort of precise map of the environment. But this is very computationally expensive, and by the time you finish producing a solution, that solution might be old news. It might be wrong. Another option that's more robotics-y is to do something like distributed sensing. So maybe we put some weather stations across the environment and we use real-time measurements from those weather stations in order to build some sort of surrogate model. But again, that requires a lot of infrastructure to be set up in order to accomplish that. So there are some scenarios where that just might not be feasible. And the last option that's definitely robotics-y is to do something like in situ sensing, where you make the weather station, or rather you make the drone or the air taxi the weather station. And as all of these air taxis fly around the environment, they are the sensors that are then combined in order to put together this picture of what this flow field looks like. But the reason I don't like this solution is that it oftentimes requires the robot or the vehicle to deviate from its task in order to capture informative measurements of the environment. It's not necessarily guaranteed that going from house A to house B is an informative path that provides you measurements that could put together a really clear picture of what the flow field looks like. So as I said, these existing methods that I'm talking about here, they rely on some mix of distributed sensing, in situ measurements from a mobile sensor, or a precise up-to-date map of the environment, which just might not be feasible. So what I'm working on doing is instead trying to reformulate the problem of predicting the entire flow field down to just predicting a smaller portion of the flow field that is centered at the robot's location. Because to be honest, that's the most important and most relevant information for flight at a given instant is what is the wind right around me, right? I don't necessarily care what the wind looks like 5 blocks away from me. And so what we'll do, as I'll talk about in the next slide, is leverage these correlations that we observe between surrounding obstacles or topography signatures and the surrounding local flow field. And then because it's 2025, we're going to use deep learning to model these correlations. Say again? AI. Yep, this is AI-enabled wind flow sensing is what the title should have been. Okay, so this is a brief overview of our methodology, right? So the inputs to our network are range measurements that you would get from a navigational LiDAR, some of which we've seen here today, and then some measurement of the flow, the wind speed, the wind flow field, either at the drone's location, which is this local wind vector, or some upstream wind vector, say from a weather station. This is kind of outdated. We kind of threw out the upstream weather station requirement later because we discovered that it really wasn't providing much information to the network in an ablation study. So we can really just rely on a single measurement of the wind at the drone's location and a LiDAR scan of the environment at that instant. And then this is important to mention, the output of our network is not just a single wind speed vector at the drone's center of mass. That's already been done. What we're doing is outputting a flow field that's kind of ego-centered at the robot at all times. So we're always trying to predict essentially on a grid that moves with the robot. And we're not just getting wind speed, we're getting components, right? X and Y components as well. And again, because it's 2025, we use AI to do this. Now, the benefits of this over some of the other ideas that I talked about in a few slides ago is that at runtime, this is very computationally inexpensive, especially in the days where we can throw an NVIDIA Orin on any of these platforms. We get a lot of GPU compute. So having a neural network running on these vehicles is really cake, right? It also generalizes to unseen environments, and I'll kind of explain why that's the case in the way we train these models. And it also requires no knowledge of the map. So you could go into a completely novel environment and have this method still run on board. As far as the negatives go, it's all of the negatives of deep learning. So we require a lot of data for our method to work. I'm not going to skirt around that. There's an inherent lack of interpretability for our method, and there's definitely concerns with overfitting to a particular map or a particular environment. And we try to do some things to avoid that. But the way we train these models is, again, it starts with a lot of data. So we developed our own in-house fast computational fluid dynamics solver that would simulate thousands and thousands of wind flow patterns in completely procedurally generated cities. So like this is like the thispersondoesnotexist.com, but this city does not exist, right? So these are all procedurally generated cities. And what we do is for each of these simulations, we do dense sampling where we randomly position the LiDAR sensor, the simulated LiDAR sensor, in the environment, collect a LiDAR scan of the environment to understand what the local topography looks like, as well as what the local wind looks like and the local flow field. And then the rest is just supervised learning, so I'll crunch through that. But we use supervised learning to train our models. And then again, we're talking about overfitting. We don't want to overfit our model to particular cities that are in the training data set. So when we evaluate or validate our models, we're testing them on much larger and potentially different city environments that we're using to essentially monitor how the training process is going. And this is a pretty cool GIF of what it looks like for the model to train. So each frame here is a new epoch or a run through of the entire training data set. And you can see at the very beginning, you just saw it for a frame, it was basically noise. But then it very quickly picks up on different symmetries of the flow. So again, this is kind of flow coming left to right over a single building. And you can see that first it kind of picks up on symmetries in the flow, and then it kind of narrows in on some finer details like the flow, the corner accelerations as the flow kind of wraps around the building. And what we get out of this is a network. Here I'm showing 3 separate networks, each trained to predict a different size environment that, again, is predicting the wind flow field, which you're seeing here in the small box in the center of each GIF, using only LiDAR sensing and local measurements, right? So that's the key innovation, is we don't know anything about the environment going in. All we get is topography signatures from these red dots, which are LiDAR scans, and single measurements of the wind at the drone's location. So again, yeah, and then feasibly, this could be run in real time using existing compute resources. So that's our method for predicting the wind. And now I'm kind of going one step further and saying, how can we use this enhanced situational awareness to actually improve the safety and efficiency of these drone operations? So the problem is, again, I present with you another situation where you've got this nasty, complicated flow field that you're trying to navigate from point A to point B. And I'm proposing that you don't know what that environment looks like. Maybe it's a hostile environment. Maybe your Google Maps is outdated, but you don't know what that environment looks like, and you don't know what the wind flow field looks like. So the question that I'm trying to address with this particular work is, how can we do this efficiently and safely? And so once again, in the same spirit as the first section of this talk, reformulating the problem from a global prediction to a local prediction, we are reformulating the problem from a global nonlinear trajectory optimization problem down to just a local trajectory optimization problem. This is still very nonlinear, non-convex, nasty problem that is difficult to solve with off-the-shelf solvers. But it's, we're able to leverage the fact that we have this new ability to predict the wind in this small box. And this is an overview of our methodology. And essentially what this looks like is we take a LiDAR scan and we feed it into this wind prediction module. And then once again, that gives us the flow vector field components in some box around the drone at all times. And we feed both the LiDAR scan and the wind prediction into a model predictive path integral controller, which is just a receding horizon MPC style control scheme that produces a higher level thrust vector command, right? And then that could be piped into whatever lower level controller, including PX4, that you have in order to get the control allocation in order to track that command as best as possible. But essentially the way we initialize our algorithm is we just give it a start location and some relative goal location, like navigate 100 meters downrange. And then we don't require knowledge about the map or any unsteady wind flow field. I want to highlight that on the right here, the simulated results that we generate are in a custom in-house simulator that we have in Python that simulates the full 6 degree of freedom plant of the model, including motor dynamics, aerodynamic wrenches, unsteady wind flow fields. So while I'm showing kind of 2D results, and it is kind of operating at a constant altitude, we are using a full 6 degree of freedom plant in order to simulate to generate these results. And so you see 2 drones here, right? The magenta drone is just interested in getting from start to goal. It has no knowledge of the environment. The black drone in this environment is aware of the flow field in the background, but only within that box around the drone, right? So it doesn't have any knowledge of what the wind looks like around it. And again, I'm using a sort of sampling-based receding horizon controller. So at every time instance, it's essentially sampling a bunch of admissible control inputs, possible thrust vectors, over some time horizon, say like a minute into the future. And it uses those sampled inputs and a dynamics model to predict where the drone goes in that time horizon. And then it takes the next best action that minimizes some sort of cost function. And I just don't really have time to talk about what cost function that looks like, what that cost function looks like today. But I'm happy to discuss details at a later date. On the right, you can see the energy consumption as a function of time. And you can see that, the energy aware drone, the black line, consistently uses less energy over time. We did some case studies, and we actually compared our method to a globally optimal graph search algorithm that's pretty popular in this literature. And so we did kind of, canonical examples of flow around buildings, around an isolated building, an intersection environment, and then one of our evaluation maps. And I just want to zoom in on this. So the orange lines here are the globally optimal solution. And the blue lines here, especially the blue solid line, is our local approximation of that solution. And so what we see in a lot of cases, not every case, but in a lot of cases, we get very similar paths traced out by our local optimizer that can, in theory, run in real time, versus the orange line, which takes 3 hours to run, right? So because it kind of checks like every possible option over and over again. So that was all simulated stuff. I want to now shift gears to talk about our more recent efforts to validate some of these ideas on actual hardware platforms. And for this, we're going to transport ourselves all the way from Pennovation, which is where we're currently at, to NASA's Ames Research Center, which is in Silicon Valley in California. And the reason for that will be apparent in the next slide. But we're planning these set of experiments that unfortunately I don't have many results to show today, but we're essentially planning to simulate these urban wind flow fields using an open-air wind tunnel, which you can see on the left side of the screen, and essentially a scaled-down mock city-style environment. And because we're kind of limited in terms of the size of the wind tunnel that we can operate in, we're choosing to use a platform like the Crazy Fly. But again, my algorithm is agnostic to whatever platform you have. It outputs a thrust vector command. Whatever drone you have that can track that thrust vector command is sufficient in my mind. But the reason we're doing these small scale environments is mostly to guarantee some level of verification, repeatability, accuracy, and interpretability of the system. So another option is I could take my drone, like I could take the Falcon 4, for instance, that's in the other room, and I could fly it around Pennovation, but I really wouldn't have a lot of confidence in the ground truth measurements of the wind that I'm getting. So by doing things in this small scaled environment where we can let it run for hours and hours, we can collect very fine scaled, accurate measurements of the flow field and use that as a more accurate ground truth that we can use to compare the performance of our algorithm over other algorithms. So again, the reason I'm going 3,000 miles away to do this is to use a really unique facility that we're currently building up at Ames. This is also half a shameless plug, I guess, or maybe an advertisement for this facility. I know that a lot of us here are on the East Coast, but my mentor at NASA that's kind of building up this lab facility, he's building it with the intent of getting a lot of people involved in this space. This is outside of the main gate for NASA, so you don't need to have any special clearances or anything, but you can come, you can bring your drone and do some free flight testing to assess your drone in a variety of different windy conditions. So this is about like a 9 by 6 foot area, open air wind tunnel, and it's situated pretty much in the center of a basketball-sized court motion capture area. Which is very unique. You don't see many motion capture areas in the US that are that big. So what this enables you to do is, for instance, for my research, set up these scaled city environments and again, run these kind of repeatable tests over and over again. So this is an example of the kind of things you can do. This is, again, a Crazy Fly. What we're doing is hovering the drone and subjecting it to faster and faster wind. I think it should pop up here in just a second here, but if you can believe it, this 30-gram drone can fly at easily 10 meters per second. Yeah, so it's essentially flying at 10 meters per second, which is just kind of wild to me that it can do that. But the reason we're doing this is essentially we're treating it as a wind tunnel, right? All of these drones are equipped with accelerometers, which are essentially, right, ways to measure the drag forces and thrust forces that each drone is producing. And so we can use that acceleration data to fit models of power consumption and drag forces, et cetera. So one of the cool things that I worked on with these first set of experiments is trying to understand the power consumption of a drone like a Crazy Fly as a function of airspeed. So if you look at a helicopter textbook, right, oftentimes you'll get curves like this for full-scale helicopters, where on the y-axis you have the power required to fly, and on the x-axis you get airspeed, essentially how fast it's flying. And for full-scale helicopters, you get some of these really neat effects where the total power required to fly actually dips for a certain speed. There's essentially a range of optimal speeds that helicopters can fly at. And what we found with our data is that we're getting very similar curves, even on platforms as small as Crazy Flies. And so maybe this isn't much of a surprise to you all, but I think everybody here is working on drones, especially autonomous drones. I think it's a really neat observation to realize that there is kind of an optimal airspeed for helicopters and drones. And I think it's something that's worthwhile investigating, especially if you are interested in applications where your drone is doing very long distance, long distance flights. The other cool thing that we can do is wind estimation. This is not a new topic or a new concept. In fact, PX4 has a wind estimator that you can use off the shelf. But the idea is these drones are equipped with accelerometers. Those accelerometers measure the drag force on the vehicle. And if you have a good mapping from drag force to airspeed, and you know what the ground speed is, you can essentially isolate what component of the drag force that you're sensing is due to wind. So instead of having a dedicated wind sensor on the drone itself, the drone can be the wind sensor. And again, that's like not a new concept, I think, for most people, but I wanted to point out that we can we can kind of easily, rapidly construct these very accurate model-based wind estimation schemes, and we can verify them because we've got this laboratory-controlled environment that we can test our vehicle in free flight, right? We're not putting it on a sting, and we're capturing all of the effects of the rotors affecting the frame, et cetera, et cetera. So that's kind of one component that I've been working on, is getting a robust, model-based wind estimation scheme up and running on the Crazy Fly. So again, one big selling point of these hardware experiments is we're going to have, verifiable, repeatable measurements that we can get in this open-air wind tunnel. And so this is just an example of the kind of city-like environments that we have. And on the right, you'll see somebody that's not me, but maybe me if I stuck to a diet and a workout routine. But somebody carrying an airspeed probe that can scan the environment and collect wind measurements all around the scene. And the result of that is a pretty accurate measurement of what the flow field looks like. This is not what you're going to get outside, because if I'm flying a drone, by the time I scan an environment with a wind sensor, that wind pattern has already left, right? The wind now looks fundamentally different than what it did half an hour ago, right? So, having this repeatability is just going to be really valuable for producing, these kind of experiments and really valuable data for characterizing the performance of these systems. Another thing I wanted to highlight is, we're using a Crazy Fly. It's a really small drone. There's no way you're going to be able to fit any LiDAR sensor on this drone, right? And of course, my algorithm requires LiDAR in order to sense the surrounding geometry. So what a lab mate and I did was we essentially recognized that we're operating in a motion capture space. We know where the drone is. We know where the obstacles are in the environment. So why don't we just spoof the LiDAR using raycasting? So that's what we did. So this is something that we're hoping to release soon that we think would be a valuable tool, particularly in education, but maybe somebody in the room thinks they might find some use out of it. But it's essentially a ROS package that uses measurements of pose of both the drone and the environment to simulate a LiDAR at a very high frequency. So you can change all of the intrinsics of the LiDAR to match your hardware platform, or you can test how your algorithm degrades as you lose more and more information from that. So it's just a really cool tool that I thought I would kind of, again, shameless plug, see if anybody would be interested in using a tool like that. But I did want to prove to you that we can get this receding horizon MPPI controller working in real time. One of the biggest, I suppose, one of the biggest issues with MPPI is that it's not real-time capable, but I just wanted to demonstrate to you that we are working on a real-time capable version of this receding horizon controller. It looks a little bit different than the simulated results that I showed you. Here, that drone is tracking this green dot, and I am moving this obstacle, this dynamic obstacle, through the environment in its way, and it's able to adjust using that fake LiDAR measurement that I had in the previous slide in order to detect that obstacle in real time and adjust its path to avoid that obstacle. All right, so I'm going to finish up, so I'm pretty much right on time. This was the outline that I showed before. If you have any key takeaways here, I'm working on methods to predict the wind and then exploit the wind, and then I have some interesting hardware experiments at the end that hopefully will be very good hardware demonstrations of the ideas that I've presented today. The key takeaways that I think are interesting to have from this conversation is, number one, these local wind flows are correlated with local building geometry because of the kind of boundary conditions that they impose. We're assuming that wind can't flow through these skyscrapers and it must flow around the skyscrapers. So if we can measure these boundary conditions, which we can using LiDAR and a single measurement of the wind at the drone's location, we should be able to exploit that to produce prediction of the wind in a region around the drone and not just at the drone's current location. The second takeaway is that motion planning in these complex urban wind flow fields can, in most cases, be decomposed into these smaller local problems that are more computationally tractable to solve. And then the third key takeaway is that, again, this is necessarily a new topic, but because of the existence of the drag forces on these vehicles, we can treat the UAV as a sensor. We don't necessarily need dedicated wind sensing on these UAVs. Let's see. Yeah, so if you liked what you saw today, feel free to scan the QR code. This is my personal website. You can use it to get in contact. I have a lot of miscellaneous projects that I think are cool, but just didn't really make it to publication. And of course, I have links to all of these papers below. And if you didn't get the QR code, it's going to slide down to the bottom left. But yeah, that's all I have.
Hi, sorry, this is more logistical. Will these slides be available on your website later?
Send them to us and we'll put them on the meetup.
Yeah.
Okay.
Question?
So I notice, at least from the visualizations you show, it's 2D.
Yeah.
Are you modeling 3D?
That's a great question. Currently, no. But there's really nothing about the architecture that I presented today that couldn't, in theory, scale to 3D. But there are a lot of more logistical engineering challenges with doing that. It requires getting even more data than I currently do with our simulations. Each simulation takes more time. I'm just a grad student trying to graduate. But in theory, like, you could scale this up and you could look at 3D simulations and full LiDAR scans. But the core principle of mapping geometry to flow fields, I think, still holds.
Question?
Yeah. Your empirical testing that you were then doing wind calculations on, was that something on board the vehicle, or is that like a ROS calculation, or?
So that was running off board, but it's a relatively light algorithm, so I could imagine it being implemented on the drone itself. And in fact, I just want to point out that PX4 does already have this style of algorithm, this model-based wind estimator. I'm not sure how many people know about it. We're using a slightly more sophisticated Kalman filter version, to maybe get some better results, but these kind of things exist.
Hey, so for the first part of your talk, you're trying to predict the local wind patterns, right?
Yeah.
And what's the backbone that you're using for that? Is that an MLP?
Yeah. And that's a really interesting discussion. So yeah, for all of the results I showed today, I'm using just a regular fully connected MLP. But I think that a different architecture like a CNN or dare I say like a transformer or something like that maybe would give better results. I'm currently collaborating with some other students at Penn to improve the architecture and start to consider some of the unsteady aspects of the flow and trying to predict not just the current wind, but also what the wind will look like 5, 10, 15 steps in the future to improve that predictive capability. But that will probably warrant some more complicated architecture to enable that.
So yeah, I think there's stuff like OGLIChem and based off physics informed neural networks, I think by Amir, that is that focuses on building these stacks. And I think you said it could run on Oren, right? And I think that's one of the benefits of your technique that can actually run on the Oren. Because none of that stuff would be able to run.
Yeah, so that can run on something like an Oren, but also the MPPI controller is highly parallelizable. So that could run on GPU and has been ran on GPUs before as well.
Awesome talk, Spencer. I love how the wind modeling ties into the simulation, ties into the prediction, ties into the everything.
Yep.
It totally makes sense to do it on a small scale like the Crazy Fly for this evaluation.
Yeah.
For all the reasons you described. But when you think about the Reynolds number dependency and how you would then translate it to an 1,000-pound eVTOL, what are some considerations you have there?
That's a great question. So a big research topic for the wind-shaped facility that I showed is understanding dynamic similitude and how small-scale environments could provide insight into full-scale environments. For instance, something that I think is really cool that I just want to mention is they're looking at trying to understand how tests at 1 bar pressure on Earth could be translated to flight on Mars. And so they're looking at using this facility to try to translate those small scale studies on a much larger scale environment. I don't have the answers right now, but some part of my thesis I think will kind of address that issue of similitude. And certainly the people at NASA, they've kind of invented the topic of similitude in many ways. So, they have some thoughts already on that.
Any other questions? Yeah.
I guess how much can you reduce the amount of LiDAR points you get? Could you have in the simulations, it's a lot of scanning data. Is there a way to do it, or have you guys tested with far fewer points?
Yeah. So on the hardware, let me pull those slides up. On the hardware results that I showed you here, if you look closely, I don't know if this is going to play. If you actually look closely, I'm only using a single scan, right? At the drone's altitude. So yeah, we're working on kind of reducing the amount of LiDAR data that you have to post-process. But again, this whole MPPI operation is highly parallelizable, including the obstacle detection. So I wouldn't be surprised if some other people are looking at incorporating LiDAR data for direct obstacle avoidance in this way, but parallelized over a GPU.
Right.
Yeah.
That makes sense.
But it's an interesting question to understand how the performance of these algorithms degrade with less and less information, for sure.
Yeah, no big thing is LiDARs are big and expensive, so you have as little LiDAR as possible. That's good.
Yeah. No, I think a really interesting research avenue is to try to do this with vision instead of LiDAR. But again, I'm a grad student, so I'm going to take one slice of that pie and go from there.
Thanks.
Yeah.
Anybody else?
Okay. Well, thank you so much, Spencer.
Cool. Thank you.